Hey everybody, I wanted to spend a little bit of time going over question number 23 here in chapter 14 of Brown-Lemay-Burston, and this is going to test related rates. I have the question up here so that everybody can see it. It's for each of the following gas phase reactions indicate how the rate of disappearance of each reactant is related to the appearance of each product. So this will, I think, help clarify how to deal with related rates. So I've taken each of those questions and I've just put it on my on my notebook here so that I can write the answers. Related rates are really what you're trying to do is determine how this rate is related to this and this. And we use the stoichiometry to determine related rates. If this has a coefficient of 1 and these have a coefficient of 1, that means all of these rates are the same. So we're just going to have to make sure that we write this correctly. Okay. So for this question, for part A here, the rate is going to be negative times the change in concentration of H2O2 over the change in time, and that's going to equal, that's all there. That's going to equal the change in the concentration of H2 over the change in time, and that's going to equal the change in the concentration of O2 over the change in time. So what we're doing is we're using the stoichiometry to come up with the new rate. And keep in mind that the rate here, let me make that a little bit better. The rate is the change in concentration over the change in time. So now what happens if we have something with coefficients? Well, I mean, what we know is these two rates are the same, but then this one is going, how do I want to say it? It's going at a different rate because it has, for every two of these guys, only one of these is being used up or is being made. So the rate is different, and that ratio can be determined by the coefficients here. So the way this is going to be is this is a negative 1/2. It's negative because it's a reactant. It's a half because this coefficient is a 2. And then so it's negative 1/2 times the change in concentration. Concentration is a square bracket of N2O over the change in time equals, and now the products, this is positive here, okay? So it's positive, and it's again 1/2 because of that coefficient. And so that's positive the change in concentration of N2 over the change in time equals, and I run out of room because I wrote big, but equals, actually maybe I can fit it in, equals the change in concentration of O2 over the change in time. Okay, so that's how the related rates are written in terms of a rate expression. Okay, let's keep practicing it. So now this is, you see this reaction all over the place in general chemistry classes. So this is the Haber process where nitrogen and hydrogen are reacted to form ammonia. And again, we're going to use the reactants and the products and their coefficients to come up with this relationship. So this is going to be the change in concentration of N2 over the change in time. And because it's a reactant, we're going to make that negative. And that's going to equal negative, again, this is a reactant, negative 1/3. And again, the 1/3 comes from this coefficient being a 3 times the change in concentration of H2 over the change in time, which then equals 1/2 times the concentration of NH3 over the change in time. Okay, so that's related rates. So now take a minute and see if you can do this. Pause, see if you can figure this out. This one should be a little more straightforward. Okay, so now let's write this. All of the coefficients are 1. So in this case, it's really just the change in the concentration of C2H5NH2 over the change in time. Now I'm going to make that negative because it's a reactant, equals the change in concentration of C2H4 over the change in time. And that stays positive because it's a product, and that's equal to the change in concentration of NH3 over the change in time. Okay, so that's all 4 parts of that particular question. So I hope that this helps you determine related rates, and if you have any questions, feel free to reach out. Have a great day, everybody.